Our final speaker of today is Peter Davies of Thales, where he's the Director of Security Concepts. He's operating at the convergence of safety and security, so an ideal speaker for today. He's an honorary fellow with Imperial College's Institute for Security, Science and Technology, and he's also chair of the AESIN Security Workstream. For those who don't know, AESIN is also under the TechWorks umbrella. It's our automotive group, which is looks at security and safety in automotive development, and there's got a separate work stream on security, and Peter is the chair of that. So if you want to know a bit more about AESIN, AESIN, you can ask me. He's a leading expert on countering cyber attacks targeted at supply chain infiltration, which obviously we've talked about this morning, on countering cyber attacks, through cyber physical attacks. He's part of the design of many of the largest scale global security systems. For example, he led the cyber security aspects of over 20 research activities, including communications, connected autonomous automated vehicles, IoT and IIoT, so it's industrial IoT, and has 30 plus years of verifying security systems in hardware and software. He likes to say that he does security where it can't afford to fail. He's sought after by organisations for his advice on their legal position with regard to cyber attack. He's based in Brighton area as well, and he's speaking remotely today. Over to you, Peter. Thank you.
Thank you very much, Mike. Can you hear me?
Yes.
Yes.
Yeah, excellent. So you obviously know more about me than I know about myself, and I'm very grateful for the introduction and the ability to speak here. This, I guess, is my short version of this thing: 2,000 plus exploits, those sorts of things, and 40 years of working in this this kind of area. And I'll try and give you a different slant, hopefully, than you've seen elsewhere, or we've been had people talking about elsewhere. I'll try and talk to you. I will use a program that we've been working on called RESAuto, which is a project that we've been doing, which was designed to look at the use of cherry technologies, which are essentially memory safety technologies, which is a hardware level of cyber security, way of achieving cyber security. And I'll try and give you some of the insights that we've got coming after that I think are interesting from the point of view of FPGAs, and that should be some of the things that you consider in relation to this. I'll try and tell you some of the things that are really good, but also some of the ways that we've actually looked at these that are designed to basically demonstrate that nothing exists in isolation. You exist as part of doing many of these things in a way that will achieve lots of outcomes. So what do we do there? Instead of looking at does Cherry do memory safety, which there are at least 160 academic papers that say that it does, we set out to look at the economic benefits and disbenefits of the Cherry approach in engineering-based and often regulated industries. Why is that important? Because if you're doing an FPGA design and you're doing security, and you do that to the exclusion of the primary things that you're trying to do, then it will make a big difference, and it will potentially mean that the work that you do is not particularly valued. And if you're able to actually bind what you're doing into what a business is trying to achieve, then that would be by contrast, that would be very important. So the sorts of things that we looked at were the implications for skills, power consumption, safety criticality, and elements of that lot. And we also looked at supply chains. So I know you've had some talks about supply chains. This was setting out to talk about when you guys put together FPGA-based components into a supply chain, it matters whether you're an IP supplier, so effectively a chip vendor, whether you're sitting there as part of a product supplier. So when we were looking at automotive, that was a tier one, but we see that in all sorts of other places, or a system integrator. At its most extreme, if what you were doing was a safety critical system and you were the system integrator or the OEM, or you did the plane, you're criminally responsible if you get bad outcomes, or at least your company that you're working for is criminally responsible. Product suppliers normally contract, and they do contractual undertakings at the level of money. And IP suppliers supply things that either need to be useful or not to the rest of the supply chain as you're going along. So very often when you talk about security, we talk about it as though it's an absolute, it's something that's really good and we should do all of these sorts of things. But we don't actually look at who benefits, who doesn't benefit. Is it actually helping everybody equally? Are you asking somebody to pay for this who may not be benefiting, in which case they tend to be reluctant? And I guess my first thing that I'd like to talk to you about here is if you look in the press, if you look in the papers and studies, you will notice that cyber is currently running at, I think, 9-point-something trillion a year in 2023 or 2024 as the losses that come from that. It is the third largest economy in the world. And if you look at Microsoft and Google, they will tell you that 70% of their problems come from memory errors. So if you put those two things together, you might presume that a hardware device that was able to sort memory errors would be worth about 6 trillion. And if that was true, I wouldn't be talking to you. I'd be on a beach in the Caribbean retired. So you need to ask yourself questions about why that isn't true. And it's down to the fact that, firstly, if you do go and ask security people, how valuable this stuff is, they tend to give you an answer that is not consistent with what the business actually understands out of that. But also your ability to realize these things without the threat moving somewhere else is by no means as simple as we like to pretend it is. That, I guess, is my short summary in relation to that. It's why we've divided things up in the way that we have. I keep trying to look at my watch to see whether I'm going to finish. So why am I looking at FPGAs? So I'd like to recommend for you a Sonata card. This comes from a company in the UK that set this stuff up as as a program, and it's essentially it's an RTX FPGA that is essentially running Cherry. If you go and look at various other places on the web, you'll find there are various people that have been doing things from smart light bulbs and all the rest of the stuff, and who argue that this solves 70% of the security problems that they get. And again, if that is true, firstly, there is a suggestion that for instance, FPGA companies should be persuaded to put the Cherry infrastructure into their library so that it can be deployed. I personally think that would be a good idea. But also, if that were true, then clearly the cost of putting an FPGA into something in order to accelerate this kind of capability being available will be well worth taking. Because if you can save even a fraction of 6 trillion, then that sounds like a really good place to be in relation to this. These boards are available. You can buy them, or if you're careful, you can maybe able to still get some of the free ones that are around. I thoroughly recommend that you have a look at these, because it's a really good insight into some of the approaches. You'll see it in the US, and you see it in the UK's assessment of how should you go forward in order to get rid of memory problems and memory problems from cybersecurity. But that isn't the whole story. So as you go for the costs of memory security, then the really things that you ought to be looking at is the balance. So I look at the interaction between safety and security. Indeed, most of the time, if any of you have heard me speak before, I like to say that security contributes to other objectives. It is not an end in itself. So it is a mechanism by which I make things safe. It is not something that I go for in its own right. But the observation that goes with that is they always entail a level of cost. It isn't done by guesswork. It's done because putting these kinds of things in there will actually put you into a better position. So it's a risk-based assessment whereby the certain cost of implementing protections must be balanced against the potential cost of an issue. That's an exceptionally difficult thing to do. So when you're recommending in your FPGA analysis, when you're recommending that you should be putting this into a component in a particular way, if you were recommending Cherry, for instance, then it would be the kinds of things that you would be looking at are those that are in the cost of protections. So this is the cost of an incident. You should be having this kind of a consideration as part of the things that you're going to. So if you're not seeing this, or if you can't derive these into your requirements, then I would suggest that you have a duty to go and try and make sure that you get more of this kind of information, because without this, it won't be possible for you to put in the appropriate level of protections for the costs that you're likely to incur. And again, this goes to the position of your organization within the supply chain. So this isn't something that you learn at university. This isn't something that it is always the same. So if you looked at for instance, elements to do with AI operation on some of the components that we have on mobile phones, and to do with cameras and things of that nature, the costs are different and they derive in different ways. They might be reputational. It might be that you don't have a leading edge product that goes in those sorts of ways. But if you're looking in terms of, for instance, IoT, and particularly the industrial IoT, then your inability to operate in a way that is safe is likely to be a consideration. So I've put up here, there are 2 slides that go with the types of questions that we were asking. So Cambridge University is a very good university. The area of consideration is a very good area of consideration. But the question that we were asking was, what do you want? Do you need these sorts of things? Are you actually going to find them into different areas? Are they being taken care of by processors that you're running on top of this? Remembering that we were using the Artix gate array in this instance to operate a low risk processor, which is a RISC-V derivative, that is essentially operating and was operating under a Linux variant in order to be able to offer user interfaces at high integrity. So very often you may find that actually components that you can't afford and you may want not yet as part of your standard element are much easier to develop and put down into a gate array based solution. So the consideration that goes with that might well mean that, for instance, you could bring a high integrity IoT component to market some years ahead of waiting for that to become available in mass components. So those were some of the things that we were looking at there. We wanted to mitigate common memory vulnerabilities and have those looked there. But our observation was in many cases that actually wasn't a problem for people who had good engineering processes. Isolation and the ability to containerize things, that started looking at efficiency compared to bare metal. How would you be able to do those sorts of things? So where do you do your security in there? The use of Cherry enabled chips in your design for more complex applications, looking at how that actually affected things like the porting of various components that you were bringing across, not just the gate array components, but the things that are running on top of that. So we are increasingly finding that in order to address failure modes, people are operating with parts of their solution operating in hardware gates and part of them operating in processors, often embedded onto the gate array. Sometimes as hard cores, but often as soft cores, because as I'll come to later, the hardware has actually proved to be a problem in the software areas. So questions like, how does it support compatibility? These are really important elements that went through with these things. And I guess I'm not trying to read down all of these things for you. What I'm trying to give you is and these slides are available. These are the kind of questions that you'd be asking about any technique that you are now trying to put into your gate array in order to try and improve the security posture. Yeah, it is really a question of whether this is the best way of doing it. Is this the most cost-effective way of doing it? So these are examples of the sorts of questions that we asked. They involve understanding of the techniques that you are putting in there. So one of Cherry's really significant elements is it uses smart metadata on the pointers, which essentially changes the size of the pointers. So imagine for one moment you were trying to put this into an eSIM that was operating on a device, and that you increase the memory requirements because of this type of technique that you were putting in your gate array. That will normally make that an unaffordable solution in the consumer area. So that would be a very big consideration. I think the last one I looked at, there were 5 bytes of memory available. And that isn't enough for this pointer-based approach to these sorts of things. So I guess what I'm advocating is when somebody says do security, it's not a question of doing security. It's whether it's being able to balance in detail the kind of questions that you would ask to be able to determine whether this is the optimum way of delivering the answer to the problems that you might have. Things like a performance overhead, energy consumption in relation to these sorts of things. Energy is a really big deal nowadays. So if it affects the energy consumption by 10%, that may in battery powered things mean that you're not actually producing a product that actually can sustain itself in the market. However, you're also looking at the tools. So this element of actually being able to look at digital twinning and simulation, as you guys would be calling it, is a really important bit of trying to get out some of these problems before you actually get to market with them. So the method that we used was this. We went through and we recommend this if you're trying to select a technology, if you're trying to work out whether your FPGA is the right place to put your security, if you're working out how the security inside that will be good. You need to look at how it may impact the costs of doing these sorts of things. And by this, we don't mean the raw cost, as it were. I think on a slide just slightly further down, which I think may be the next one, we'll talk about the fact that we essentially looked at a 7.2% increase in the cost of developing software was a typical impact that we saw from putting a Cherry enabled capability into our gate array here. So that's 7.2% on the total cost of developing a product, not just the gate array, where it may well be more efficient. However, on the products that were running on top of it, they had an increase of 7.2%. That's more than the Chancellor has just put on national insurance that is seeing all that press. So consider it in that kind of way. This might be the difference, certainly in certain low margin products and in certain low margin areas, between a product that can be successful and one that can't. So it's very important that one considers those sorts of things. So it's also really important to understand what is the existing approach that you will be using around these sorts of things. So I think when I spoke last time at this meeting, I talked about the sorts of approaches that Talos goes through, the way that we actually look at how we do things inside gate arrays. That includes how we will achieve safety critical, how we will do supply chain sorts of things around this sort of stuff. This fits on top of that, and you have to be considering, how does that change what I would otherwise have done? Or are you telling me that this is a complete change and we could not have done this otherwise, which I guess enables complete new markets, in which case those are the sorts of things that you need to understand when you're putting these things there. The cost drivers, and a costing exercise where you often go through a finger in the air estimate based on. So we do our technical parts very well, but we don't really look at the costs and understand what it will take inside an organization to scale up. So we went through a process of understanding here, what would it take to scale up 10 of our FPGA engineers so that they were in a position to properly support this, rather than carrying on doing the things that they've been doing up until that time. And that was a very significant overhead, both in lost opportunity, but also in other elements. But the outcomes of it, we have concluded that we should not do 10, but we should do 4. So we basically looked at, there are really good use cases where this should be used, and we should be using this, and we will be able to use 4 of those engineers to achieve that, and they will be best positioned to do that, and also to advise. And this value is obtained by can be improved over time by obtaining quotations and writing and getting different things along the way about how you can do these sorts of elements. How do we do this? What we looked for, and we note that in many engineering firms this is missing. We had access to metrication of currently anticipated costs to achieve cyber safety. And we also had access to costs of ensuring business outcomes. Or to put it another way, we were able to assess whether the techniques that we were expecting to use from an engineering point of view, in this case specifically Cherry, were likely to have a positive or a negative outcome in relation to the through life safety and cyber safety, and our obligations in relation to that, bearing in mind that nowadays, if you're a product supplier, you've got things like the European cyber directives that you need to comply with. And as I say, going through the systems that use those sorts of things, you have other sorts of costs that actually sit alongside that. And we saw insurance as very important. We weren't looking for cyber insurance. What we were looking for was the insurance that we take against business continuity, which essentially is, for a cyber event, what have we got that we're actually trying to cover in the event that we get an outlier that is really bad. So those sorts of things. And actually that meant that we were able to measure, and I advocate measurement in all cases, measuring what you think we will achieve for cyber resilience. So when you're talking about a technique of this sort, what would that mean? It's not just a question of can I do it? It's really much more a question of should I do it? And given there's almost certainly somewhere where you should do it, should I do it in this instance? So as a good quality FPGA engineer, being able to operate in the area of cyber and safety, these are some of the questions that you really should put yourself in a position to be able to answer. And these are some of the ways that we approach being able to do that. And then the most important thing there, where and how would the hardware security need to be integrated into the engineering and business act to realize these cost benefits? If you get it in the wrong place, you just can't realize the benefits, no matter how good you are. And I'm sure you're all excellent, but no matter how good you are, you won't be able to get to that. So I've put up here some of the characteristics of safety critical systems. It's high levels analysis based on safety standards. Things like ISO 26262, things like the equivalent avionics standards, provenly low failure rates, including the impact of memory safety, the use of proven in-service methods, deterministic behaviors. These are the sorts of things that our engineering practices in what I would term the traditional engineering industries have set out to achieve. By contrast, if you were looking at what have we set out to achieve when we're doing another app that's running on my mobile phone, it very seldom sits into these characters. So that is one of the reasons why it's much more likely that if you were deploying these sorts of technologies into a mobile phone area, or if you were throwing it into an IoT device that is essentially consumer electronics, it would be highly likely you could realize benefits, whereas many of the techniques you've already used in safety critical and particularly control systems engineering will likely have already taken care of a lot of these sorts of things. I'd like to actually highlight, if I may, some of the things that we saw as really important. So one of the things that we got out of this, and Cherry is an excellent technology, it does memory safety. However, it significantly increased the risk of denial of service. We went through those sorts of things to look at that. It also invalidated many of the fault-tolerant design patterns that people had been using. Yeah, so it was very difficult to use. So to put that into context, where in fault-tolerant and safety critical designs, you essentially often have two implementations and a checker. Cherry made it possible for us to fail each of those simultaneously, where previously they would have failed statistically in sequence. So it essentially gave you ways of calculating how you could operate. And if you think about this, very often for control systems engineering, you're looking at how do you operate under failure. And this took away many of the arguments that you would have wanted in relation to that. So the fact that actually we couldn't point at anybody else doing that sort of stuff meant that you were pioneering, which essentially meant we believed that we could only use this in areas where the biggest outcomes were to be achieved, and where it was most difficult to actually do something currently. And imposing lockstep execution imposed a choice of Cherry behaviors. So often people implement into hardware lockstep against various things. But imagine if what you've got is two pointers that in software are taking radically different things. What that meant was, what that would mean, for instance, is that you could persuade it, or you could put it into a situation where to operate in lockstep, you have to have taken care of the worst difference in performance between the two devices, and for that reason you often got only about 10% of the performance that you would normally have anticipated out of a hardware implementation. That would be a drastic disincentive to the use of this type of technology, and these are the sorts of things that we were going on. And we talk about brittleness because it's one of the fundamental concepts that I use in security. You can make things strong, but your question is often, what have you made brittle when you have made something strong? That is a really significant thing that you get out of that. From a regulated point of view, we looked at how did these sorts of things address threats, and where did they go to? And often what that means is you're trying to map down to various things. So these look like TARAs and HARAs, and that's a really important point. If you're trying to do security and you're trying to support safety, you've got to fit into the methodologies that people use for doing those sorts of things. So it's only part of the solution. And I have to say, I'm trying to use Cherry here as an example. It's one that we've had a really good opportunity to work on. As I say, it's a really good technology. So 196 academic papers aren't all wrong. They're absolutely right. It's a good technology, but it isn't necessarily the right technology to be chosen from an engineering point of view. And as I say, comparison then with other ways of doing that, it's 40 years, that people have been doing these things. There's been memory safe software languages. There's been other ways of doing things. So pointer authentication, canaries, memory tag. You could put all of those things in there instead. So it isn't a question, and this is almost always the case. It's not a question that there's only one way to do this. It's always a question that what you're looking for is the best way to do this for your application. So this is part of what we did in relation to this. So just to give you an example of the sorts of things that we looked at, we analysed and modelled under a parametric model the cost trends that were associated with these things. The blocks that you've got over on the right hand side of the slide, which I hope are big enough for you to read, but if they're not, you can have a look at them later. Essentially looked at the ones that have got stars and blobs and things against them are the ones that were touched by this. So the observation was when we started putting things in like this into an FPGA, how that impacted on the engineering process in order to model and in order to be able to get the benefits was extremely widely distributed across the entire engineering process that you needed to do. Or to put it another way, doing a good job in the FPGA will often not be followed by the rest of the business being able to take advantage of it. And that's why we came to, as I said previously, our analysis here in a fairly standard case was a 7% increase in costs of a deployment. That's a large increase in costs. We also noted, as we went through this one, that the skills didn't exist. So the types of things that we'd expected, we expected that the memory safety in hardware would radically reduce the level of skills that we would need to produce good quality things. That is the kind of things that often we hope for when we put things into hardware. That was not the case, and indeed we determined that we needed to go and deploy some of our most skilled engineers. Furthermore, the way in which it failed meant that many of the processes were, as opposed to allowing you to simulate the whole thing and then go through and go back to it, we were essentially being stopped every time we hit an error, which is which I guess is a very 1980s way of doing these things without many of the advantages you would get. And I would observe that is exacerbated if you're trying to use AI in order to demonstrate your validation against these kinds of things. And when we were looking at what we were trying to achieve, it was very salutary to remember this is a slide that essentially talks about the fact that hardware has been just as bad as software in actually producing errors out of these things. So one of the observations we got back from our safety critical people was, you just put me in a single point of failure for my entire system, and I'm going to find that very difficult to cope with. So we had to cope with that, and we had to understand what that would mean in trying to put these things forward. And I'm almost at the end, I think, of my presentation. Just looking at things like the volume effect. Generally speaking, if you're trying to innovate new processes of this sort into your FPGA design, or indeed anywhere else, you don't get the volume effect. You don't get the tools around this thing. You can't easily pick up skills around those sorts of things. So you need to be considering, when you're pioneering in this way, the payoffs that you can actually get out of that. It's often better to be a little way behind, and that allows you to take advantage in the development of tools in these sorts of areas. In this case, we considered that the tools were available to use, but too fragile to be used in an industrial context. And these were just a couple of general observations that we put there. So security and functional safety are considered as just part of the general hygiene features. And that unless it has a specific dent, there's no reason to put it in above those sorts of levels. It's costly enough to do that. And cost isn't a suitable defense for a failure. So if I go to court, the fact it would have cost me more doesn't work in a criminal, it doesn't work in a criminal court. It also doesn't work under contract law in the event that you're going to be in the event that you've contracted to do something and you then found out it was too costly. So you need to be looking at those sorts of things in relation to that. And in relation to the automotive, this observation that regulations, and it's very similar. It's what you're seeing on the Cyber Resilience Act. It's what you're seeing on the other acts that are coming out of the EU and elsewhere, which incidentally you're signing up to if you do a CE, are essentially mandating through life protection against cyber. So finding a way to be able to do this, that is probably changing the economics of how you have to offer cyber into your safety solutions and your product solutions, which may mean that you move towards these sorts of things. I'd like to thank a set of people here and give you a set of which I'll leave there as part of it rather than reading them out. I also have to thank UK Research and Innovation for helping us to put some of these things through. And I've got to my thank you, and I don't know that I've seen anybody ask a question, which is always a bit of a result for me.
You should be looking more closely, Peter.
Sorry?
Yeah, a couple.
Okay. Are these in the chat? He says. Or...
I know that's in, so you might have got away with it after me. Yes. Okay. And we will finish there. We'll give Peter a thank you.
Well, thank you for giving me the opportunity, and I apologise that my travel unhinged.
Not to worry. We thank you for being online instead. And just to give people the good news, we are going to be at Tyler's next year, aren't we?
You are. We're working to make sure that we have a date that's suitable, and we shall look forward to welcoming you again. Yeah.
Perfect. Okay, I'm going to share the screen and just finish off from here. Can you see that, Tisha?
Yes.
Okay. So thank you for everyone today. I'll just remind myself of the speakers. So starting from the end, Peter, thank you to Peter, Tobias of Synopsys. We had Espen from EM Logic in Norway, Andrew Swirsky from BeetleBox, who was here in Cambridge, Ian Pearson from Microchip, who is also here in Cambridge, as was Flaming Christensen here in Cambridge, and of course Peter from Brighton. Thank you to our sponsors, Synopsys. Alex Grove is here if you want to speak to Alex. And Christensen's here from St Duns. And of course, TechNess or TechWorks. And you've heard of also ITSF today and our AESIN networks, as well as our TechNest networks. TechNest will be changing its name. You'll see a bit more detail on that, but there's going to be a lot more what we call the design network. And we've got a kickoff in February the 8th in Reading. We should be talking about design flows that based on that around AI. I think Cadence, Synopsys are there, and potentially Siemens. Plus ARM. We're going to talk about chiplets and about how that affects your AI implementation in silicon. And we've got Accelerex, sorry, who do a IP AI accelerator. So it'll be in Reading, and we'll send you the information on that. I think it's 8th of February, it's early February. All the presentations from today will be going online on my webpage, my company webpage, Alpine. Send me ideas at my TechWorks email address. I consult into TechWorks and help organise these events. And this is what we've got coming up. I mentioned these before, but I'll just quickly go through them again. The one in Renishaw was very popular last year. You had a lot of people online and very positive feedback. So it's about how you can start to use AI in FPGA, both in development and in your products. And that was specifically asked for Renishaw, who are looking to see if they can enhance their FPGA through AI. Then we've got verification futures. at the University of Reading on the 1st of July. But there'll also be IP companies, about 80 students from UK ESF. There'll be the FPJ stream. There'll also be people from what we call ChipStart, which is the silicon catalyst, which venture funded semiconductor startups in the UK. And it's kicked off from the States, the Valley, and now we have it in the UK as well. It's called Silicon Catalyst. If you want to look it up, and they'll be there. The day before, we're going to have some tool vendor days. So we'll have some of our EDA vendors and potentially some of our IP companies doing training on the day before. So that'll be Monday, June the 30th. There'll be a barbecue the night before. There'll be university accommodation available. So hopefully you can spend the day at the University of Reading. On the Monday, doing some training, on the Tuesday, joining our event. And for those who remember Silicon Gorge, which was the football competition in Bristol, that will be running in Reading on the Monday afternoon. So a good couple of days out, hopefully. The students will also be doing posters. So we're going to run a student poster competition. And there will be about 80 students looking for jobs. Okay. And no, sorry, and then we're coming back to Cambridge. So we want to build up our network in Cambridge. It's our first one here. So thanks for everybody attending. And next one will be more around technology roadmaps. Microchip hosted that this year, but we're going to try and move it to Reading and talk about the ecosystem around the FPGAs. And then we will be back at Thales and on FPGA safety and security, who are sort of our natural host for that. And that will be in Q4. So thank you very much. I think lunch has arrived. I just checked lunch. And we get kicked out of here at 2 o'clock. Thank you very much.
Thank you, Mike. Thank you, everyone, for joining the session.
Yeah, it's all through there. So feel free to go through.